In technique 1, we used simulation to characterize the runtime of our functions. In technique 2, there will be no simulation at all. Instead, we're going to build a model. That is, we're going to use our human brains to look at the code and think, what's important about this? What is it that will affect the runtime? And in particular, our model is going to be, let's fix the input to be some array of size 10,000, let's say, and let's count how many times each of the different operations occur. So for example, how many times does I equals 0 occur? How many times does j equals I plus 1 occur? Less than, plus equals, equals, and array accesses. And together, those things constitute everything we might need to care about with the runtime of this function. So let's think about it first. How many times does I equals 0 occur? How many times is I initialized to 0? Well, it turns out that will only happen once, okay? And hopefully you agree with me on that. And if not, pause and think about it. And so we'll move on to j equals I plus 1, which will be a little more challenging. So how many times does j get initialized to I plus 1? Well, even at this point, these counts are going to start getting tricky to compute. This one will be tough, and these will be really tough. Okay? So let's start with I plus 1. So we figure, okay, in the very best case, there's a duplicate right at the front. So in that case, I equals 0 happens, then j gets set equal to 1, and then we immediately return true. So in the very fastest case, it will happen exactly once. But in the worst case, well, when I was 0, j got set to 1. When I was 1, when I was 1, j got set equal to 2. Then when I was 2, j got set equal to 3. Then I got incremented. Then when I was 4, j got set equal to 5, and so forth. And so this line of code, you can realize, runs once for every number between 0 and 9,999 and 10,000. Now, if you didn't follow every word I just said, it was maybe a little tedious. That's fine. And I'll give you a chance shortly to be able to do your own. But this is the exact number of counts that this operation occurs. And whether or not you fully get that right now, no big deal, but I hope the idea makes sense. Okay, how about less than? How many times do these less thans occur in total? Well, in the very best case, they happen exactly twice. We set I equal to 0, we check, okay? We set j equal to 1, and then we check, and then we immediately find a true situation, and then we're done. And in the worst case, it will actually be 50,015,001. Now, where did this number come from? I'm not even going to talk about it. It probably took me 20 to 30 minutes to figure out these bottom four. And that's just how it's going to be. And luckily, later in this lecture, we'll talk about, well, we don't really care about the exact number. We'll get there. Okay, how about the increments? What turns out that can happen between 0 and 50,005,000 times. Equals, a little bit less. And array accesses is exactly double the number of equals operations. Okay. So hopefully it's clear what we've built, even if it was a little tricky to imagine how we got these numbers. So what's good about this approach? Well, the great thing is it's machine independent. It does not matter what computer you run your program on. This is the number of operations you will get of each type. Now, I'll say just very briefly, to be pedantic, that's not 100% true. On a modern computer, there are issues like branch prediction, where the numbers can be a little off. But that's actually okay, because this is just a model. Just like we don't have models that are perfect for how our airplanes or our cars work, or how any number of other things, vaccines, whatever else. We don't know exactly how these things are going to work, but the models are going to be good enough to make useful real-world predictions, and the same is true here. Okay? Another great thing is that the input dependence is captured in the model. With the simulation, well, it depends on whether or not you ran it with an array of all duplicates or not. That will make a huge impact on how the functions will run. But here we can actually just capture it and say, well, there's a really fast case and a really slow case. Now, there are some bad things, right? First and foremost, it's tedious to compute. So tedious that I didn't even show you how I got these because I found it so tedious. Another thing is that the array size here was arbitrary. And then lastly, it doesn't actually tell you the actual time it takes. So it's harder to interpret, to really feel good that you've come up with something. When I tell you an algorithm takes 3 seconds to run on a certain input, it's like, okay, clear. This is a little stranger. And you might imagine, right, just for those of you who are thinking ahead, what if I know less than takes a nanosecond and equals takes like 3 nanoseconds or something? Wouldn't I be able to somehow plug all this into an equation and get a time? Turns out you can't, because modern computers are too complex. They have features like branch prediction and caching, things far beyond the scope of the class, where you can't actually get the actual time, even with some magic equation. Okay. but that's just a minor digression. The important thing here is this is the model we built, and it tells us some important things about the running of DUP1. Okay, now, to address the issue that 10,000 is a totally made up number, and to make our technique even better, we can actually compute what I'll call the symbolic count. Here we imagine, rather than having an array of some fixed size, say 10,000, we imagine, okay, for an array of size n, what would we get? So for j equals I plus 1, it'll be between 1 and n operations, or this operation will occur between 1 and n times, and so forth. And we end up getting all these expressions. Now these are even more tedious to compute than these over here, and so that's a negative. But what's good about this? We'll start with the good, right? I mean, that's a nice thing to do. So it's still machine independent, that's great. We still have our input dependence captured in the model, but in addition, this now tells us how our algorithm scales, right? We don't have just some arbitrary number here. We now have an equation, something that says how many less than operations happen as a function of the size of the input. That's going to be something so important to us. Now the bad thing is that this is incredibly tedious to compute. These expressions are horrible, but again, later we'll talk about how we don't need to actually derive these full expressions. And then we also have the same issue that it doesn't tell you the actual time. So this new technique, this modeling-based technique, it's ultimately we're going to be using, and we're going to try and understand why scaling is so important. But before we do that, in the next video, I'll give you a chance to try and do this exercise on a less tedious function to make sure you get it. So I encourage you to check out that video, and we'll come back to why scaling is important after that.